Welcome to the second week of the exciting topic, digital signatures. What we did last week, we gave an introduction to digital signatures, and we did actually more. We started talking about security services, which is an important topic, blah, 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 blah. And then algorithmically, we did RSA digital signature. And today's lecture is a direct continuation of that, so kind of the most important thing, the most important basic elements we had last week. What I would like to do with you today is mainly two things which we split into three chapters today. I want to show you an attack against RSA digital signature. That's what we did towards the end of last week, and I couldn't squeeze it in last week. And then maybe the main part of today's lecture deals with another signature scheme, Elgamal digital signature. And then after introducing digital signature, which is not all that complicated, I want to talk about things you have to watch out for, things where you can make mistakes, weaknesses, / attacks. Okay? So the attack against RSA, and it's not like an attack like factoring, which is, it's pretty easy to protect against. You just choose really large moduli and you're fine. This is kind of built in, and it's built in a lot of digital signatures, and it's kind of interesting to see what can happen with the construction we had. And it has a really fancy name. It's called existential. I don't know what the German translation is. Maybe existential, but it doesn't really fit what it is. Existential forgery. Forgery is Fälschung. Attack against RSA digital signature. So let's look at the protocol again. It's kind of fun. So what I'm going to do now, I just draw the protocol from last week, Alice, Bob, and then we add Oscar, and we look what Oscar can do if he is, if he wants to do bad things. So we have Alice. We have, I think I'll do that on the next board. You need at least 1/3 of a page if you're copying. If you towards the end flip over, half a page would be better. So we start with Alice and Bob. So if you look up how RSA digital signature works, it works quite similar to a regular RSA encryption scheme. So Bob computes a public key, which is the modulus n, and the public exponent e, and he keeps a private exponent. Then he distributes his key openly over the channel. And then what he normally does, and you can copy that. Then in order to sign, he simply takes a message X, erases this to his private, his secret exponent, and that's it. And then he sends over the channel X, comma, signature, right? Okay. So. And then what Alice does upon reception, that means if she gets message and signature, how do we call that? What does Alice have to do? What do you have to do with the signature? Verify, right? You know, the signature and verify. So Alice verifies. And you notice that here's, you know, in 2 minutes we're going to, Oscar is getting active. So as Oscar is going to do really bad things here, so leave some space, right? 8 Kästchen. Okay, so verify. So what does he do? What does she do? She takes the signature, raises this to the private exponent, to the private key power, S to the E, modulo n, which we call x prime. And does anyone recall what is now the last step? You know, you all did homework last night, right? So what was the very last thing you did for verification? How does Alice know that the signature is correct? Yeah. Exactly. This x prime, which she kind of recomputed, she has to check whether this is identical to the original message. So here she has to perform a check, is x in fact identical to x? Okay, so that's it. So what we do now is we switch colors. We see what Bob can do with this protocol, okay? And now the goal is Bob wants to, Oscar, can you read the green? Is it visible on the board? Not so good. Red? You can have red. Okay. Okay, so let's assume this doesn't happen. Let's assume, so what I'm trying to say, Oscar is not fiddling around with a message that Bob actually sends. What is much more attractive for Oscar is that he generates a message with a valid signature, right? So one possible scenario is if Alice is a bank and if Oscar generates a fake message, transfer 1,000 euros from Bob's account into Oscar's account, signed by Bob, right? That would be a nice attack. So let's see whether Oscar can do it, and he can almost do that. He gets pretty close to it. Okay, so what Oscar does for this existential forgery attack is first step, he chooses a signature S in Zn, so you know 0, 1, 2, 3, 4 up to n minus 1, and n is a 2000-bit number. Really large number, okay? And secondly, Oscar computes x is equal to S to the E. Does Oscar know E? Of course, it's a public key, right? This is in reality, this is Bob's website. Okay, so this is no big deal. So he takes E, he takes N, which is on Bob's website anyway, and the S he just chose, and then he computes X. Okay, so what he then does, he sends X and S to Alice, except he is not using orange chalk. You know what I'm trying to say? So he said, you know, orange means, oh, it's bad, it's coming from Oscar. So what he really does, he's sending this message and say, hey, I'm coming from Bob. You know, he uses like Bob's IP address or email address or whatever identifier, okay? So what I'm trying to say here, Alice thinks, well, this is coming from Bob. It says, I'm Bob, I'm a message from Bob. I'm a bank transfer generated by Bob. So what Alice wants to do, she wants to verify, is this really coming from Bob? So what does she do? She does this operation. So now what we are interested in is question: does the verification check out here? Does the verification check out? Sorry. Does the verification check out? Does the verification means, is this verification process correct? The problem is x prime, which Alice computes here, is computed as taking this s, raising this to the eth power, from coming actually from Bob, and Alice gets x prime out, and then, and what is x? X was computed by Oscar. According to this formula. So this is the x prime that Alice, this is Alice. This is Oscar. They compute the same thing. Okay? This S and this S is the same, this E and E, this is E the same, the two N's are the same. Okay? So what means this is a valid signature. This is a problem. Oscar just generated a valid pair message signature. Oscar cannot, which Alice does not detect, so she thinks it's a valid signature. Okay, there's a problem. This is bad, and now I want to talk with you about it. I want to start a discussion. What is the limitation of the attack? There's some from Oscar's side. What is kind of not so nice for Oscar with this attack? Any ideas? Yeah?
Oscar can choose what X looks like.
Yeah. What does Oscar does? Oscar chooses the signature, which is kind of weird. Normally, what Bob does, he computes a signature. He doesn't care what the, what kind of the semantic of the signatures are. The S, for instance, ASCII meaning, right? So he chooses S, which he doesn't really need to know, but this is not the problem. The problem is, what about the message that Oscar computes? Well, the message that's being computed is S to the E, which cannot be controlled. Particularly, imagine E is a really long number, 2,000-bit number. This is like RSA encryption. So what happens is the outcome to Oscar looks like a pseudo-random number here. You get the random number out, and in particular, it's really hard for Oscar to generate an X that looks like, please transfer 1,000 euro into my account. Let's say in ASCII here, right? So this is a problem, okay? So limitations of the attack. Oscar cannot directly control the semantics, but Bedeutung, meaning, the semantics of the message X. So now, and you could say, okay, this is kind of more or less a theoretical attack. You can run the attack, but it probably doesn't have much meaning in the real world. Nevertheless, it's still very annoying because it's still, if this is a computerized system, which it probably is, it does it automatically. It's not very nice that this is, cryptographically speaking, recognized as a valid signature, where in fact it's not. You can do a denial of service attack. You can probably mess up a lot of things. And so what we would really like to have in cryptographic terms would like a signature where this is not possible, right? Where the outcome is not, hey, I'm a valid signature, and it's not a valid signature. So the question is, are there any countermeasures? And there are. And what we really start doing here, and it's almost the first time in the lecture, when we talked about RSA so far, and I think I mentioned it once or twice, is the plain old RSA that we did initially. This is often called schoolbook RSA, meaning this is a basic principle, this is how it works, it's very important to understand, and this is how people invented RSA originally, right? But then it turns out in practice, you cannot use plain old RSA the way I'm usually presenting that here in the blackboard. In the real world, you have, for instance, this attack, and you have to change RSA, how it's being used, okay? And this is maybe the first time we really get away from these very basic protocols and give you a little bit of an idea what kind of other things you have to watch out for in practice, okay? And this is one example how you can change schoolbook RSA, okay? Should we continue that? Okay. So what you can do, and there's actually a very nice countermeasure. In practice, what's often done, how you can prevent the attack, is you impose heißt auferlegen, erzwingen. You impose formatting rules on X which can be checked by Alice. What do I mean by formatting rules? So the idea is, in schoolbook RSA, what you have here, what are the requirements on X here to sign? There are no requirements. You take a 2048-bit number, whatever you want. It can be an email, it can be ASCII text, it can be a graphic file, it can be compressed data, which are more or less random bits. Whatever you want, raised to the d's power, you get S out, okay? And now we change that in order to prevent that attack. We say, well, we don't really allow any X, but only certain X, So what we say, and this is a very simple example. In our textbook, actually, there's how you really do that. Okay, there's a really complicated way of formatting that. But the simple idea is, there's an example. So we have now X here, and we say the payload, die Nutzlast, means the actual message is M. Okay, as before. This is whatever you want. This is your email, this is your graphic file, your compressed data, whatever you want to encrypt. But it's not the full length. Let's say we have, if the overall X is, let's say, 1024 bits, we say, well, we only allow the payload, the actual message, your email or your PDF file, to be 900 bits long, okay? You have to pay a price for this formatting, for this added security, so we're not using all bits. And the remaining bits, this is the padding. you impose an arbitrary bit pattern, and to make maybe things easy, we say, okay, we want to have (124) ones there at the end. Okay, we say every message that L assigns has this format: 900 bits, whatever the payload, what you actually want to not encrypt, what you want to assign. We don't care what that is, but the trailing bits, the last bits, the LSB bits, least significant bits, are 100. They're all ones. Okay. Now, if this is a formatting rule, Oscar has the following problem. Oscar computes and he essentially gets random values out here, X. There are random 1024-bit values here. And now, now we can do very basic probability here. What is the likelihood that the LSB, that the last bit is a 1? What would you say? 50%, right? S he can choose, but if you raise it to S to the E mod n power, you get something random out. So he can choose an S here, he raises it to the E's power, and maybe he gets one with a 1 out, maybe with a 0. If he gets something out with a 0, he chooses a new S. He can do that, right? You just choose a new S, he gets the same. Okay, so he needs 2 trials on average. How many trials does he need to generate a 1-1 at the end? Any ideas? 4, right? I mean, what is a possible bit pattern? 0, 0, 1, 0, 0, 1, and 1, 1. 1 out of 4, If you want to have 3 ones, you have a chance of 1 out of 8, right? That means on average, Oscar has to generate 8 different S values to get this bit pattern. So, and you get the idea, right? He needs 2 S's, 4, 8, 16, 32, 64, 128, 256, 512, 1024, 248, blah, blah, blah. How many trials does he need to generate 124 bits here? Any ideas? 2 to the 124, right? And, this is close to number of atoms on Earth, right? This is a really bad number, okay? So, he has a chance of 2 to the minus 124 to have a message X with 124 trailing. Trailing means am Ende stehen, ja? Trailing ones. Okay? Remark. See textbook for real world padding. Schemes. They are much more complicated. This is the idea. Okay? So, I'm going to show you that board again in a minute. So, we're done with chapter 1. It wasn't that difficult, right? And I promised you last week, from now on, things become lighter. We're not doing much more new mathematics. We're not doing much more brand new crypto primitives. We use pretty much what we have around. Okay. So what we want to do now is, second chapter is Elgamal digital signature. Okay, and why do we do that? What we've done in this, really since the last break or since late January, we talked about public key. We did public key encryption, we did public key exchange, now we do public key digital signatures. And there are always these three families of public key algorithm, right? There's the RSA family, integer factorization-based schemes, and that's what you learned. So you saw how you can digitally sign something based on the integer factorization problem. Why integer factorization? If you want to really break that thing, deadly break, you have to factor n. Okay. But you know there are two other families of public key schemes, the discrete logarithm schemes and elliptic curve schemes. And we're not doing all three this time, but I want to show you one more, namely one discrete logarithm-based scheme for building digital signature, and this is Elgamal. So this is chapter number 2. Elgamal, digital signature. Okay. So we immediately jump in this protocol here. So again, we look at Alice. In a fair amount of space. I mean, I took me almost half a page to draw this protocol. So if you want to copy. Okay. So as you remember, all public key schemes have a setup phase, which we kind of skipped over. We just said, well, Bob has a public key and Bob has a private key, and now we want to kind of show, we want to do the same here to start with. So we have the setup phase. It's a discrete logarithm problem, so what we always need is a cyclic group where the discrete logarithm problem lives. So we choose a large prime, we choose a primitive element alpha. And what is a discrete logarithm? Discrete logarithm is always something like right? This is the setting. And we have x and y, and one is the public key, one is the private key. What is x? Is the public key or the private key in this DL systems? It's a private key, right? Discrete logarithm problem, it's called discrete logarithm problem because it's a problem to compute a logarithm. It's difficult. Computing logarithm means it's difficult to compute the exponent here. Why am I saying that? If we now generate our random k private, which we call lowercase d, kleines d, as always, essentially from ZP, but we kick the first and the last element we kick out. So if this is a private key, the private key always shows up just call that DL. So this is how DL problem looks, right? The private key comes always goes in the exponent. Okay, and that's alpha is essentially the public key, and we can now send over okay, public really consists of this triple, namely the actual public key, this beta here, so that would be this is K public. So beta is kind of the real public key, but also these parameters, the prime and the primitive element we're working with. So this is a setup phase, right? Or key generation phase, it would probably be a better term. Okay? And now things start to get a little strange, and this is, or I should have said that before. If you compare RSA digital signature to RSA encryption, it's really difficult. Hello? If you compare RSA digital signature to RSA encryption, the stuff we did in January, February, there's hardly any difference. It's almost the same. This is different here. So Elgamal encryption is actually quite a bit different from Elgamal digital signature. Now we start. One thing that is different, we always have two public keys. Okay, we have this beta, which is kind of the real, the long-term public key, but we also have a public key which is unique to every message. So for every message, so this is beta, which Bob always needs. It stays with Bob. But then every time a new message is being generated, he needs also a new temporary private key, temporären, zeitweisen public key. Okay, now let's look how the signing goes. So we are kind of this part of the protocol. Here signing was really easy, it was just one exponentiation, and now it's getting a little bit more complicated with Elgamal. Okay, he has now an ephemeral, so a really fancy word for temporary, zeitweise, is ephemeral. Ephemeral key, which is key sub E, which is actually notation we use in this lecture in the book. Normally, I don't know, I don't think it's used otherwise. And again, that's a message specific. This is for one signature, you need one ephemeral key, and afterwards you have to throw it away. ST means such that, so das. Okay, I'm running out of space. Okay, such that, so das. Okay, with the additional condition that the GCD, the greatest common divisor of this ephemeral key, the key we just computed, and p minus 1 is 1. Okay. Okay, so now on parameter E is being computed. Which is alpha to the ke modulo p. So this is another discrete logarithm we compute. Not all that surprising, maybe. Coming back to this condition here, what about this condition here? We had this condition before, this GCD equal to 1 condition, right? If we have that, what can we say about ke and p minus 1? What happens? When did we use this? This is, they're relatively prime to each other. When did we need that before? Yeah? Exactly. The inverse of ke exists, right? We have an inverse, okay? So we have an inverse of ke, and we are going to use that now for the second part of the signature. The second part of the signature is S minus D times R multiplied by the inverse of ke. Okay. So these two parameters, this was a setup. This is the signature. So this is quite a difference from before. Before the signature S was just one value, was one 1024-bit value. Now, signature is 2024-bit values. But besides this, the protocol just follows this basic rule. Bob signs, he sends over the message together with the signature, which now consists of two parts. Okay? Don't get confused, signature consists of two parts here. What does Alice have to do? We saw that before, Bob signs, Alice verifies. So this is what, ja. Ja. Nee, da ist irgendwas falsch. No. Very good. Very good. Excellent. We need the tag, we need the message, right? So this is my mistake. Okay. Again, to make it abundantly clear, this is the signature here. This signature is R and S. Okay, now upon reception, Alice has to verify. What does she do? She computes this auxiliary Hilfsparameter T, which is beta, which is the public key, raised to the rth power multiplied by r raised to the f power mod p. And now she has to check whether this t is equivalent to alpha to the x mod p. If that's the case, we have a valid signature. If this is not congruent to alpha to the x, it's an invalid signature. I put that up for you so it's easier to see and copy. Seems weird. And I don't, well, you probably in your lives, that means if you stay in your favorite bachelor program here in IT security, you're going to see more discrete logarithm protocols in other lectures down the road. To do this proof of correctness, it's pretty easy, and it's actually kind of fun. What you do is always substituting stuff, and this is what we're going to do. We want to check, does this verifying make any sense? Okay, and we call that proof of correctness. So we look at what Alice is doing, and does this verification decision, is t equivalent to alpha to the x? Does this make any sense? Okay, so what Alice does is she computes beta to the r times r to the s. And now we substitute. Where is beta coming from? Beta is alpha to the d, right? You see that up there somewhere. So this is alpha to the d raised to the rth power. What is r? R is the first signature parameter, right? You see that r is alpha to the ke. Everybody with me? It's just substitution here. Okay. Now we go back to 9th grade. This is my son Noah is just doing Exponentialrechnung. This is, the same base alpha, so you can put all of that to the in one exponent to the base alpha. So this becomes d times r plus Okay, E times S mod P. Okay. Now a little intermezzo, Nebenrechnung, remark. Okay. In order, what we need at this point, we need a theorem we had many weeks ago when we did prepared ourselves for RSA. We had this Fermat's little theorem, which I just call little Fermat, which sounds cute, niedlich, right? So it's Fermat's little theorem. It's not the big Fermat's Vermutung. Okay, so what Fermat essentially says is a to the p minus 1 is equal to 1. You know, this is what he observed in the late 18th century, 1790 around. Okay, so 200 something years ago. But from this, it follows if you have an arbitrary exponent m, you know, not p minus 1, but the m is in any integer, we can write this as m mod p minus 1 and what's happening here is maybe I skipped it. I don't know whether this is. Let's write that differently. So this is. I'm sorry. I skip things. So this I can write as a multiple. You know, m is a multiple of p minus 1 plus some residue, some remainder here. Remainder. This is it. So what I'm doing here, I'm splitting m into multiple of p minus 1 plus r, and then I just rewrite it in this form here. Okay. Now if I take this is just algebraische Umforming here. There's no number theory or anything fancy. This is just plain. This is 9th grade. Okay. But now if I apply to this expression, if I apply modulo p, whatever I raise to the p minus 1 power, including this expression, becomes 1. Okay? So this, I'm getting rid of this. So what we have left here is this a to the m is identical to a to the r, and a to the r is only the remainder here of this expression. So from this, it follows that a to the m is identical to a m mod So what does it mean? And this will be very important for the rest of your life, so to speak. You know, for the next 2.5 semesters till you get your bachelor's degree here. Okay? So whenever you do modulo p arithmetic down here with the real variables, if you have exponent, and p is being a prime, and in the exponent you can do arithmetic modulo p minus 1. Okay? You know, this will stay with you till, you know, you get your degree here. So, and this comes handy here at this point here now. So we do modulo p here, but what we want to essentially, you know, process the exponent, work with the exponent from here on. So what we can do at this point here maybe introduce here and we have to show that this is equal to alpha to the x, so we have to look what we, or should we use a different, yeah, we call that x, that's fine. So from this now it follows that d times r plus pe times s is identical to x. So we compare the exponents, and from Fermat, from little Fermat, we saw that we are allowed to do mod p minus 1 arithmetic when we work with the exponents here. Okay. And now we just do some simple reordering. Okay. So what you see here is this is exactly the construction of S by Bob here. That means, and this was the condition, this is here. Verification condition, right? That was a Bedingung that we have a valid signature. This is coming from here, okay? And now we played with that. We said, okay, if this is a verification condition, what happens with the exponents? We got this equation, and it turns out we get a correct verification if S is constructed in this way. And this is exactly what we did, okay? So the verification process is correct. This is a proof of correctness. If you have exactly this, L beta to the R times R to the S, which seems kind of weird. If you do that exactly this way, it turns out, and S has this form, the verification is correct. Okay? One practical remark here. The signature R comma S, is really those two parameters. Has twice the bit length of X, which is not very pretty, but something we can live with, and I guess we have to live with. Just to give you an example here, it's not very complicated. So if we have a If you have a 2048-bit prime for our discrete, where our discrete logarithm problem lives in, then these bars, these are striche here, right? These are not parentheses. You know, this means the length is 2 times 2048 bits, which is 4096 bits, okay? Just to give you an idea what that means, okay? Signatures get long, and if you do that on your internet, you don't care because you're permanently watching YouTube, right? Where you get a few million bits per second, or maybe a million bits per second through DSL. If you want to have a digital signature on your bank card, this is more of a problem because here, it might take maybe 4,000 bits is what you get over the channel in 1 second. And if you have wireless cards, without contactless cards, it might take a few seconds to pump the bits over. So what I'm trying to say is that there's certain situation where it's not nice to have relatively long signature, in particular on small kind of devices. Okay, so this seems a little weird, but it's interesting. In plain old Elgamal, the stuff I just showed you, is not that very widely used. But, and this is a good thing, there is this was a remark, we call that remark 1. Second remark, Elgamal digital signature is the basis for, it's the base, I guess, it's the base for DSA, which is a very popular digital signature algorithm, which is widely used. Okay, so there's RSA out there in the world, which is probably the most popular signature algorithm. And then there is DSA, and there's an elliptic curve version of that. Okay, so DSA is quite popular, and it's based on what we just did. So when we go back to our to-do list for today, we're done with Elgamal digital signature. What is left now, and it's actually kind of fun, I hope it's fun, we want to look at weaknesses, at attacks. Okay, so this is chapter number 3, weaknesses of Elgamal digital signature. Okay, so we're going to look at this board that we have over there, and actually I'll start on I start with the, we look at 2 attacks. I don't know whether you want to call that attacks or weaknesses or pitfalls, whichever term you want to use. And the first thing that we do is we look at the reuse of the ephemeral key. What I mean by reuse means we're using the temporary key twice. And why would we do such a stupid thing? Well, there's a pretty good reason for that, for trying to do that. If you look at the effort, it's a computation, the delay, whatever, the work Bob has to do. We have to set up the parameters. We don't really care because you only have to do that once, and then that stays with Bob. Beta, this alpha to the d, he only has to do once, that stays with Bob. So this whole setup phase, we don't really care about speed or effort, right? Because you only do that once when you set up your system. What really hurts is everything, it starts from here, the signature, doing the ephemeral key. And now let's maybe look a little bit at the algorithms we have to do. So what does Bob have to do to compute R here, alpha to the ke? What kind of algorithm is he using at this point? What is that called? Square and multiply. So this is one exponentiation, which is not good. This is pretty intense. And what does Bob have to do to compute S? Well, he has to subtraction is not bad. One multiplication is not bad. Another multiplication is not bad. But how do we do this here? What algorithm do we use for computing the inverse here? Very good. This is EEA, extended Euclidean algorithm, which is not that easy either. It's also logarithmic complexity. So both of these operations are pretty painful. Okay. And when does Bob have to do this operation? Well, every time he has a new x, every time he wants to sign a message, he has to generate a KE, he has to compute R, he has to compute R with an exponentiation, he has to invert KE. So if it would be possible to reuse KE, that means using KE not for one message but for two messages, he doesn't have to do exponentiation, he doesn't do the inversion. That means the second signature would be very, very cheap. Okay? So it's tempting to do, but it's really stupid. And I'm going to show you why. Don't do that. Okay? The ephemeral key, this temporary key, really must be unique to every message. Okay? So assume Bob uses KE for two messages x1 and x2. And again, the reason for doing that, a computational would be easier. And it's not completely obvious because, of course, the R would stay the same. If KE is the same, you get identical R cells. But the S's are still different because the X is being used here. Right? If you have different messages, you still get different S's here. So you might think it works. Okay? But now what's being sent over the channel, so what Oscar sees is he sees X1 going over the channel together with R and S1, and here R is identical, right? I don't call that R1 or R2, just call that R because this is the same in both cases. So he sees that, and then the second message that he observes has the same R parameter, but a different S here because the X's are different. What he would really like to know, what do you think is a big prize? What is a really cool thing to know for Bob? The private key, which is somewhere here, D, right? So, and now let's see, can he construct the private key? And in fact, he can. It's not that complicated. So he takes, of course, these two expressions here. Based on these two expressions, he looks at this here. Right? He looks at the construction of S. He knows S1 was being constructed as, you just use this expression here. This is X1 minus D times R times the inverse of the ephemeral key, mod p minus 1. He gets a similar expression for the second signature. And now you have a system of equation. You can solve the system. Blah 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 blah. This is really simple. I'm skipping over this. This is a good homework assignment. He ends up that. What are the unknowns? Maybe we can argue this way. What are the unknowns here? D is unknown, but you can get rid of D here. Okay, So you can get rid of d times r, and you end up with an expression for ke. Okay. Again, this takes 2 minutes to derive. This is very simple. So now he has the ephemeral key, which by itself is maybe not that spectacular. What is very nice for him to have, though, is once he has ke, he can go back into any of these two equations, and he can solve, maybe I copy the first one. So what is known in this equation? Well, he knows S1. This is going over the channel, right? He knows X1, which is also on the channel. He knows R, which is on the channel. And what he didn't know before was KE, but he knows that from here, from the first step, from the first calculation. So the only thing left is, the big prize is D. And he gets that. So D, which is the private key, if we reorder this here, it becomes X1 minus S1 KE divided by R mod p minus 1. So it's really simple here. That's what I just showed you. It's really simple to compute that. And now, once he has D, hell is loose. Die Hölle is los here, right? He can do whatever he wants pretty much. In particular, once he has a private key, he can do the thing that we couldn't do with the existential forgery attack. He can generate a message, please transfer 1,000 euros into Oscar's account. Why is that? Well, now he has D. Now Oscar can pick a random KE. He can do this computation. He knows the square and multiply algorithm, right? He buys our book, right? And he knows how to do that. Or he goes on Wikipedia and knows how to do that. And with D, he can now also generate S here. Okay? So once he has D, all is lost here, right? Oscar has all the power. He can completely behave like Bob. It's really bad. Okay? So, what is the morale? Moral der Geschichte is don't reuse, right? Don't reuse the ephemeral key. Pick a new KE every time, and I'm sure there will be homework assignments on that. Okay? Now the second attack we wanted, maybe write it down. Do not reuse the ephemeral key. Okay? So the other attack I want to show you is along this line is an attack similar to what we did with RSA. It's an existential forgery attack. That means we can also show, and I'm going to show you now, I can show that we can also generate, Oscar can also generate valid signatures, but with the same problem that he can't really control the message. But it's possible. Okay? So that was, if you want to use numbering, that would maybe be 3.1 here. And that would be chapter 3.2. Elgamal, existential forgery. attack. Okay, we immediately start with this protocol here. So we start with our two personae, Alice and Bob. Bob has K public, which is a triple P, alpha, and beta. And the private key D, and Bob distributes this key. Okay. And now what he then normally does, he does all this stuff here, right? So this was the setup phase. And then what he also does, he does assigning here. Okay, and now we're going to show, which color did we use? We used orange. Let's stick with orange so we, keep a consistent color for this type of attack. So now we introduce the third party, the bad guy Oscar. Okay. What does Oscar? So Oscar's goal is again to generate a valid pair, valid triple really, a valid pair X with a signature so that the signature checks out with Alice, for Alice. Okay, so the first thing that he does is select integers I, j, I und j with where GCD of j and p minus 1 is 1. So probably we have to want to invert j at some point down the road, okay? Then Oscar computes the signature. This R, namely as alpha to the I times beta to the j modulo P alpha hoch I mal beta hoch j and S in kind of a tricky way. This is minus R times the inverse of J mod P minus 1 Well, any idea why we're doing that? Well, we're going to see in a minute, but this complicated method we do so that the verification later checks out. Oscar knows, Oscar is watching the video later on the internet, right? So he knows this is what Alice is doing, right? He looks in any textbook. So what he has to do, he has to compute R and S so that this check gives a valid result. And this is where they're coming from. And we're going to see that in a minute, okay? So once he's done with the signature, and this is similar to what we did with the RSA attack. We also, we computed the signature, except in RSA it was trivial. Computing the signature was choosing a random S, okay? But then once you had a signature, you computed, what did Oscar compute here? The message, right? Which is not what Bob normally does. Normally you have your message, you compute a signature. With this existential forgery attack, you do it the other way around. Same here. Once Oscar has the signature, in the third step, he computes the message. namely x, the message is s, times the parameter I, mod p minus 1. Okay, now he's sending all that stuff over. Means he's sending over x and r comma s. And what Alice computed, and should probably switch colors now, because as before, he's not using orange chalk. This is not an orange message. This is a white message, right? So this orange means I'm coming from Oscar. This message, of course, in a heading, it says, the header would say, hey, I'm a message coming from Bob. So what Alice does, Alice gets a parameter, she wants to verify, she's following the rules. So she computes beta to the r times r to the s mod p, and she will see that this is t is in fact identical to alpha to the x mod p, and therefore she concludes this is valid. Valid. Signature, which is bad if you're a good guy. So, I'm going to fit it in here. Yeah. Why does the attack work? So let's see, kind of proof of correctness of the attack, but it's kind of funny to talk, with correctness of an attack. So again, we have to check that if Alice does this parameter, she gets a true statement out. So this is t is equal to so this now again we only do substitution. We look what beta is. Beta is alpha to the d to the r. Alpha still beta still comes from, it's the original beta from Bob here. That's a discrete logarithm problem. Times r times s. This is alpha to the d times r. And now it's getting a little messy here. R is this expression. And I continue here, otherwise I'm running out of space. So I'm just, substituted here, this here, and now beta is beta. Beta is alpha to the d. Everybody with me? Is that too fast? Yeah. that beta is alpha to the d to the j, so I get really bad exponents here. So, and this becomes this is all 9th grade, right? This is just dealing with exponent here. There's nothing crypto. Okay. Now I'm looking, I have to look what S is. S was minus R times inverse of J. And again, S is the inverse of J mod P minus 1, but this is the proof we showed before with the a little Fermat theorem. Fermat's little theorem is if I do arithmetic in the exponent modulo P, I'm allowed to do exponent arithmetic mod P minus 1. This is what I'm doing here. If you multiply this in here, you get d times R and what's happening here is so you multiply this in here and this becomes minus dr j times the inverse of j mod p. I can do that. So what is j times j minus 1 mod p minus 1? What is this here equal to? It's 1, right? So here we have minus in the exponent minus d times r, and we have plus d times r. So they cancel. Okay, and now I have this additional condition that this is S here, this part is S, Rj minus 1, so this becomes alpha to the Si mod P. But Alice checks. So everything we did so far is we computed an expression for here. Okay? So we found out blah, 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 blah. What we just showed, it took us half a blackboard here. We showed this ends up being equal to alpha to the S times I. Okay? Why is that cool? Because in the next step, she checks whether this is equal to alpha to the x. So now she checks t is alpha to the si. Yeah. And now she checks here at this point whether this is alpha to the x. But what is alpha to the x? Well, x was constructed as s times I here. Similar to what happened here, if Oscar computes a message as s to the eth, and later on Alice verifies s to the eth, you get the same expression. Similar thing happened here. This is far more messier, right? We need whatever, 6 lines or so to do that. But it turns out, this is all simple arithmetic, it turns out, at the end, we get this expression out for t, that means for beta to the r times r to the s, we get this out here, and this is exactly the way also x is being constructed here. Okay? That means this looks like a valid signature to Alice. Again, what is the drawback? And this is probably more dramatic than in the case before. No, it's similar here. Oscar cannot really compute the outcome of x here at this point. That's his problem, right? Because he can choose I so he has control over I, but S is constructed in particular from R, and R is alpha to the I, beta to the I. That means he cannot really control what S is. Okay, so similar outcome as before. Can he generate valid signatures? Yes. Can he control the message? No. So he can essentially pseudo-random messages in X, he can sign validly. Okay? That's it for today. Thank you very much.